Hello community, so great that you are back. Now, today we look at context length. How can we extend the context length, for example, of a Llama 3 8 billion free trainable token that has originally 8K token length? How is it possible that the model can now handle 2 million token? Now, you know we have here the large language model and then we have the vision language model. And we are not talking now in the first step about here, how is it possible that we can put 2 hours of video in a Gemini 1.5 Pro system, but we want to focus here on the language models. How is it possible? The Llama version 1 had 2K, Llama version 2 had 4K, and now the latest Llama version 3 has 8K context length. How is it possible to jump from 8K to 2 million context length? Now, there are a lot of methods. Some are basic, some are advanced, and some I would not recommend at all. So if you see here, somewhere on the internet, a model with 2 million, and they give you here a brief explanation how they did this, after this video, you know if you should use this model or not. So, let's start here. It is China 2021. 4 years after we had Attention is All You Need. And we have here Shui Yi Technology in Shenzhen, and they published something amazing. They did something about Rotary Position Embedding. And you would say, yes, of course, we know we are working here with transformers, so we have the self-attention mechanism. In the original paper from Google, we had here the absolute position embedding that happened here with sinus and cosinus functions. And then they worked here through other papers at this time, and they had a great idea, a new main idea. They tried to publish this. Then they calculated their idea in a two-dimensional case. They found a general form, and they wrote here in the annex of this publication a proof that this is really the correct solution. And you know, this is the way that we learned RoPE, the Rotary Position Embedding of our words, of our token, when we do the self-attention calculation in our classical transformers. Now you know me. I care about my young green grasshoppers and I tell them, hey, be smart. Today you don't have to go this hard way, because today there's a much better way to learn all of this. At first, let's think about absolute. Do we need an absolute encoding in AI? Now, there are cases where we say, yes, there is an absolute that makes sense. We have 0 Kelvin, minus 273.15 degrees Celsius. This is 0 Kelvin. We do not have minus 1 Kelvin. It does not exist in physics. So there, this makes sense. But if we look at self-attention and a classical transformer, for the easiest case now, we do not need an absolute position encoding of our tokens. A relative position is absolutely enough, because what we want, if we have a sentence here, and we want here to calculate here the attention score to the other words in the sentence, we just need to know, okay, this word is 10 words away, and maybe this word here is 3 words away. So you see, a relative position is all that we need. And this does not limit us here to an absolute context length that happens during the pre-training of our LLM. So this is nice. But if I would explain this to you today, there's a much simpler approach. Look at this. You know, to calculate the self-attention, we need an inner product. And we need the inner product of a query and a key. So what we have here a function that encodes here the position information of a query and a key, f query and the function for the key, and we have here a word embedding of a specific token at the position m, let's say 17, whatever it is. So you have an xm and you have here an m. And then you have another position, n. Now, this formula is all that we need, because we need here to find a function g that captures here the inner product here, with this parenthesis, between the query and the key, encoding their relative position information in a form so that the new function g on the query and the key depends only on the relative distance m minus n of here the positional encodings. So you see, this is now our system that we need to solve. This is the main idea if we switch from absolute position encoding to relative m minus n position encoding. Now you can check your books of mathematics and you know there's one solution to this system of equation. There's one solution, and this is a beautiful solution because mathematics, pure mathematics, without any knowledge about AI, tells us, yeah, in function theories, we know that the solution to this equation, the function f of our query and the function f of our keys at a specific position m or a specific position n, has to be in this form with a complex exponential. And then we have here the position m for our queries here, and then we have here a theta. A theta can be a scalar, or it can be, later will become a function that we optimize. So just from pure mathematics, if this is what we want to achieve with an relative position encoding and embedding in the attention mechanism of the transformer, we just have to solve this equation. And this is the solution to this equation. Now, if we put this in, we get now our function g that we need with the relative positional encoding. And since we're operating here on a complex exponential function, we take here, just to be sure, the real part of this. And then we have exactly here a complex exponential that depends only on the relative distance of our words or of our tokens in the sentence. And this is it. I just need here 3 lines and 1 page to explain to you the rotary position embedding, given that this is our main idea, and Matt tells us this is the set of mathematical solution that will solve this equation. So you see there's some linear transformation you can have to your queries and to your keys, but this theta will become very, very important later on in the video. For the moment, it is a predefined non-zero constant that we set to a specific base. The base that RoPE used in the original publication was 10,000, and this theta has some beautiful properties. So where we are, we say RoPE, our rotary position embedding, that we encode not only the attention, but also where are our words in the sentence, that the system understands how far away are other tokens, essentially rotates the query and the key vectors in our high-dimensional space by a specific angle. And this is not a normal angle. This is a mathematical angle in a complex exponential function. So we are operating here not anymore only in the real vector space. And this angle that is rotating here in the mathematical space is proportional to their relative position. So simple, the rotation, theta, incorporates the relative position information. So what we achieved just by adding here one boundary condition on our system, and this is the most important set of equations that you need to understand RoPE. This is RoPE. Because look, we know here with Euler's formula that maybe you have seen this in a simplified form. You know that the complex exponential can be understood using Euler's formula from 300 years ago. And they state, hey, I can write this also here in this simplified form, cosine theta plus I complex sinus theta. And then if I've solved this, I can have here an interpretation that this now, cosine and sinus, is now a rotation. And in the context here of our complex plane, please remember, we are not working here only on the real space. Cosine could represent the x-coordinate and the sinus could represent the y-coordinate, and the term I represents here a 90-degree rotation, because you remember multiplying by I corresponds to a 90-degree counterclockwise rotation in the complex plane. And therefore you can say, and this is a correct statement, multiplying a complex number z by complex exponential I m theta rotates z by an angle m theta around the origin of the complex plane. So this idea of a rotation, I've seen many ask, how can I imagine this? You can't really imagine this because we are operating here in a pure imaginary mathematical space. This is not only the real part. We have to extend here to go a little bit further. Okay, and now we go to higher dimensions. Now, if we have higher dimension, and remember in the simplest case of self-attention, we have a transformation to go immediately after the input encoding to a high dimensional space. So this is a beautiful idea now. We divide the embedding space that is now 1024 dimensional into, this is D half, 2-dimensional subspaces. So what we do, we take the complete space that we have in our solution, the complete embedding space that we built, and we construct now, if it's a 1024 dimensional space, 512 2-dimensional subspaces. Because we have found the solution for RoPE, the Rotary Position Embedding, in a 2-dimensional subspace. And now what is easier to say, hey, I don't see a 1024 dimensional complex space, but I see 512 spaces, each of a 2-dimensional complexity, where I know the mathematical solution to the equation. So you see, this is something that is beautiful, and this opens up here the gate to a further understanding. You see, it is simple. We just have this simple mathematical 2-dimensional RoPE solution, and we operate with this. And now we have 512 subspaces. That makes it so easy to computational find here the solution. So in this subspaces, but let's look only at one subspace to make it easy. We know that this is now here, the complex exponential is now similar to a rotation, and this is the rotation matrix in a 2-dimensional subspace. Theta, very important, is the rotation angle. We have specific values are chosen for desired properties. And m is simply the position of the token, so we encode here where is it. And then, when embedding xm at a specific position m, RoPE modifies it as follows. So we have now that RoPE tells us, hey, we apply now this solution, this rotation matrix here, and we find a solution. And we do this, and remember, we had a function query and a function key for both functions. And if we then calculate here the inner product with RoPE, with the relative position encoding, our inner product that you see here, and you remember, was equal a function g. Now we know the solution to g if we input here the function q and the function k, and you get here an expression with the rotation matrix structure. And if you look at this, you have now the rotation that depends only on the relative position n minus m. And this is what we set out to achieve. So you understand, without any other theory, that we can calculate now the inner product for our self-attention mechanism with this new relative positioning, RoPE, and we have here a rotation matrix, and this is beautiful. But as always, remember the query vector, for example, here f of q, is expressed with both the real and the imaginary components. Do not simplify this, that you try to understand this as a rotation only happening in real, because this is not what it is. And now there's another beautiful thing that is coming up of this RoPE publication. And you know, if we have the solution in a two-dimensional space, and we have 512 spaces of those where we know the solution, so how do we build now the complete rotation matrix for all our 512 spaces? And it's so easy. Look at this. The complete rotation matrix, if we apply this new RoPE idea, in higher dimension, let's say we embed it in 1024 dimension, is a sparse. So this means we only have a little bit of data and the rest is zero. A block diagonal, so those non-zeros are primarily in our diagonal of the matrix, where each block is a two-dimensional complex rotation matrix. And this is what makes it computational, if we go to our GPUs, so efficient to apply now this rotation also in the high-dimensional embeddings. And this is exactly, and I have here the original paper where they show you this. Look, this is our complete rotation matrix. You see it's almost zero everywhere. Exact in the diagonal structure, we have our two-dimensional matrix elements. We have it for theta 1, for theta 2, then for theta 512. So you see, this is now a computational simple structure, and this is exactly what we need, and this is RoPE. This is the rotary matrix here that we need. And you might say, this looks amazing. So the parameter I have to care about is theta, because you see you have theta 1. So you have for each subspace of each our 512 subspaces, you have a specific rotation angle theta. Yes, and this is exactly why we did this. This is a property that we want. So now let's focus here now at the next part only on this theta, because theta is extremely important. Why we need it? We want to have unique positional encodings. The primary goal of theta is just to ensure that each position in our sequence that we put into our LLM has a unique encoding. Otherwise, different positions might end up with similar or real close embeddings, and we do not want this. We want to have a clear separation, we want a clear clustering that is happening, and not everything is smeared together real close. No. This theta determines here the amount of a real complex rotation, and this rotation is related to the position of the word of the token that we encode. And if you choose theta well, and this is now an art, before I show you how to do it in a program, this theta leads to a better attention weight of the system and it improves here the complete model. And now you might say, why do we have different rotation angles in different subdimensions in our 512 spaces? Now this theta was originally by Google, in the original attentions all we need, had a base of 10k, 10,000 here, to the power of minus 2j divided by here our dimension, 1024, where j is now the dimension index. And remember, it goes from 0 to 512. Now, this specific formula is highly intelligent chosen because it ensures that different dimensions, so each of our 512 subspaces, has a different rotation angle. Now this creates a hierarchy of positional information with a geometric progression of frequencies. Real simple. What is a geometric progression of frequencies here? We want to probe the system here with different frequencies. And you know, and I'll give you an example in astrophysics in a second, that higher frequency components capture finer positional details. You have a high frequency, you go up about, yeah. So whatever is positioned real next to each other, you can resolve here that they are not one point, but they are two separate entities. Now, if you have a lower frequency, this component capture here the positional patterns that are more on the global side, not on the local side. And if we combine this multiple frequency approach here from our rotation angles, this allows the model to encode here both the local and the global positional information effectively. And this is beautiful. We don't have one frequency that we analyze the complete system, but we have a complete set of multiple frequency that we can define with this carefully chosen theta definition that probes now the system. And this is one major part, but there's also a second extreme important case. You want a specific property that is called a long-term decay. So now in this definition of theta, inherently it has that the inner product between the query and the key vectors, if we do here our RoPE calculation, it decays as their relative distance increases. And this makes sense. Imagine you have at the beginning of a book an introduction, and then you have the end of the book. After 500 pages, you have, and the murder was Jones. Now, for this system to get and understand and have a causal reasoning, you want that local information, like what's here on the screen, has a stronger correlation to itself. So those words taken together, they explain something. But if you take the beginning of a book and the end of a book, you want that there is a decay the more distance you bring into the system. And this aligns what we have in our natural language, this property that distant words are less likely to be related. So you see, this theta, this specific definitions, gives us a multiple frequency analyzer for our semantic content to calculate here the attention scores, plus a long-term decay. Isn't this beautiful? Just in simple definition. So what we can say now, we can say that theta j represents the frequency that is very specific for the jth dimension. And every dimension has a different frequency. So higher j values correspond to higher frequency, resulting in faster oscillations and narrower pattern detection. And the opposite. In RoPE now, the higher frequency results in a faster oscillation of the sine and cosine functions, enabling the model to detect narrow, fine-grained positional patterns, and the opposite. So you see, this multi-frequency approach is so beautiful. Think about astrophysics. You have ultraviolet and you have the infrared light. And you know that the infrared light here has longer wavelengths. And if you have an astrophysical object like a nebula with a lot of gas, interstellar gas somewhere, those infrared lights, they carry some information. Those can penetrate here obstacles like interstellar dust clouds, and therefore we see in the infrared spectrum more details, what is behind a specific dust accumulation, than if we would look at this only in the ultraviolet spectrum. So you see, those frequency analyzers, This is so important to detect here objects in astrophysics, and we use kind of the same idea now in AI. So there we have it. Now in version, 5 or 8 of this specific paper that I showed you, and the latest version I could find was now November 9, 2020. We have now rotary position embeddings for self-attention in transformers. And now for RoPE, look at this. I just wrote here for you 10 formulas and you understand everything. I start here with the definitions of the embedding. Then, as I told you, we want to calculate here the inner product, where we only want that the most important boundary condition is that it is a relative position in the result. We found that we have rotary matrix structure. We know that we have a sparse block element here in this diagonal structure of our complete rotary matrix, where this is here exactly for the subspace 1, let's say of our 512 subspaces. So we use the two-dimensional solution for each of those 512 subspaces. You can calculate it. You found the relative position embedding. You can find this in the self-attention. You remember we have an orthogonal property of this specific matrix because we operate in a mathematical system. You remember Euler's formula where I showed you either you can see this as here as a complex exponential that is mathematically much more elegant, but if you want, you can see this as a rotation with cosine and I sinus. And this is the general form for higher dimensions. So RoPE, if you understand here, the basic principle is relatively easy. And RoPE is the base for everything that happened afterwards. Without RoPE, we would not be able to talk about how to extend the context length of our LLM or vision language model. And in this latest paper, they show here RoPE here just with this set of equations. So you see, whenever you understood what is the core of RoPE, you can write it in whatever form you want. Here the cosine and the sinus. Beautiful. Now let's focus again on this theta. Short summary, of course, short interrupt. Why we have this specific form, and I told you already some reasons. And this specific theta formula was so important for attention to work, so that we can add the positional encoding here to the attention mechanism. So each dimension of the positional encoding varies at a different frequency. We have 512 subspaces, and each subspace has a different frequency. I showed you with this definition on a base of 10K, we achieve a geometric progression in the angles. This is something beautiful. With this particular form, and especially with this base, and we will modify the base a little bit later on, we can make sure that all our positional encodings are orthogonal and unique across different positions, which is beneficial for self-attention, but is essential for self-attention because you can have two positional encodings with the same value. Plus, I've shown you that this ensures an exponential decay in the positional frequency if we change the dimension. Plus, each dimension captures a different periodicity in the positional information. Like in the astrophysics, I showed you, if we go here with longer infrared waves, we have a different periodicity, and we find here more details what's happening behind an interstellar dust. If we go here with ultraviolet, we can't look through this nebula. And you might think that the base of 10K is somewhat arbitrary, but later when I show you here this theta scaling or theta extrapolation, we will modify the base. So all of this will become important later because those are the parameters that later on the authors try to optimize. And this is RoPE. And this is a beautiful mathematical thing. But later, in a dark, stormy night, it happened. Some other group published something. But yeah, I have to show you. Here we have a publication of Meta. When Meta Platforms Incorporated says, hey, this is really complicated, no? Can we find a way to extend here the context window of an LLM? We are something that we don't have to do all of this pre-training, you know? Can we kind of cheat here our way into those extended context length? What do you think about position interpolation? And with this here, it happened that a non-real, logical, mathematical deduction happened, and some people tried to have some beautiful ideas so they do not have to do all of what I just showed you. And in this study, Meta tells us, hey, we achieved that we can go here from a 2K context length for the original one to a 32K token length here if we do here some supervised fine-tuning. So, to my knowledge, they were the first to say, listen, we don't want to do this whole pre-training here on a long context. And no, I imagine this would be costly. We would need days and weeks of compute infrastructure. But what we do, just a fine-tuning, and somehow we managed to get here an 8 times extension. And this was amazing. And you know what they said here? You know what? This fine-tuning, we don't have to run the complete cycle. We only fine-tune it for some steps here to achieve a good quality result. A good, whatever is good here in mathematics. But then they say this here really clearly, Meta. And the cost of this fine-tuning, this method that we apply, is nothing compared if we would really do the system from scratch, from the beginning, with a 32K context length. Like it would be mathematically sound and absolutely the correct way to go. No. We don't want to pay the training cost, says Meta, with how many billions in profit? So no, we don't want to pay this cost. We just try to cheat and we do a little bit of fine-tuning and we will have a good quality. And this opened the box of the Pandora because now everybody said, hey, if Meta can do this, let's try something even more crazier, no? You see what I feel about this? Let me give you an emotional depiction of this. So this original Llama model had a 4K token context length, 4,000 token are here in this little green box. And the idea was, hey, this works great. For Meta, in their business plan, they say, hey, we have Facebook. So yeah, people do not post Facebook comments that are more complex than 4K token. So if I apply AI for Facebook, a 4K token length is perfect. Instagram. I don't even need 4K token length. Why in Instagram? People go with much less if I do AI analysis. I can put here, 10 or 100 Instagram posts together to apply my AI system that has a 4K context token length. The same for Threads, the same for WhatsApp. Hey, this is a 2-second goldfish memory that I just need. So for Meta, it made sense in a business case to have the original pre-trained model 4K. This was logic. This was perfect for their business application. But then some other guys, let's call them Google, said, hey, I have a 1 million token context length in my system and I can analyze video. So the idea was, now hey, you are not the only company in the world here that you say, okay, I have 4K and the other has 2 million or 1 million token context length. Yeah, this looks a little bit unbalanced, no? So what we do? Now, if we look here at this 4K from Meta, let's look at this. Now RoPE is the solution, okay. So we have here from our pre-training our LLM, we have the so-called pre-trained range of 4,096 tokens, 4K token length. since we are working here with sine as and cosine as an orthogonal system to do the positional encoding, what do you think we just extrapolate this? Let's say to 8K. That sounds good, yeah? And you might say, yes, you have a periodicity in the system, so for a certain extension and certain extrapolation, maybe there might be some indication that theoretically it could work. And Meta said, hey, great, so if I have now 8K, but my pre-trained range is just 4K, so what I do? I take here this 8K and I squeeze it into the pre-trained range, which was 4K. So in the range where the system works, I know this, of 4K, I have now squeezed here the extrapolated part also into, and now in my green 4K interval, I can have 8K tokens. Now there might be theoretically an idea that you say, okay, at times 2 extrapolation, that is again interpolated here, and we're talking here about positional information, might, yeah, if you squeeze it in, a factor of 2, maybe. Now, it is not a factor of 2, it is a factor of 4K to, let's say, 2 million tokens. So now they tried to take the 2 million tokens here, to extrapolate to 2 million, and then to squeeze everything, this 2 million length, you squeeze into this little green box. Now you're not gonna believe it, but this did not really work out well. And you said, amazing, no, how is this possible? If I take this and I squeeze it in this, there could be some degradation in the performance of the system? Okay. So the simplest approach, what we call today position interpolation, to be absolutely correct, to compress here this sequence here to fit within here our green trained interval, maybe not so good, or as it was explained later on by another research team, this can be problematic as the IDs are squeezed into a small range, a really small range, providing especially difficult for the high frequency dimensions. So you see, there was a kind of critics that said, maybe this, what they call here position interpolation, PI, yeah, there might be some limits to this. And a little bit later on, we have a group, News Research, Eloite AI, University of Geneva. They said, we can increase the efficiency. We're still talking about here window extension of our LLM so that we have a larger context window for our LLM. But we think here this interpolation is not really it. We try now something that we call a neural tangent kernel theory. And they call it YARN. Yet another RoPE implementation. And in this paper, I recommend you read this paper, they also say this interpolation, this position interpolation of Meta is insufficient. No, but who cares? But if you really want to read an interesting paper, 3 years before YARN, I would recommend you this paper. This paper is absolutely unknown, but it is about the Fourier features that let the network learn high-frequency function. You remember in RoPE we have those in a low-dimensional domain, and we are operating in a 2-dimensional domain. So this idea, and yeah, of course, UC Berkeley, Google Research, and San Diego. If you want to read a paper about this and about NTK, I would recommend you to read this very early paper because this is really interesting. Okay. But then, of course, yes, February 2024, we have Microsoft entering the stage and say, hey, buddy, I have the solution. I know how to do this, and now I present to you long RoPE. So we are extending our LLM context window beyond 2 million token. And we know how to do it. We looked back here at RoPE, we look back at the interpolation by Meta, we look back here at different other methodologies that appeared in the last 2-3 years, and now we have the solution for a 2 million token context length. And this is the end of part 1. It would be great to see you at the beginning of part 2.